Good morning, students. Yes. So in the previous class, we have discussed about path difference and air wedge, right? In second unit about interference. So you would have studied what is called interference and what is called air wedge, right? So we have seen that experiment and the not experiment, theory of that wedge-shaped film we have seen, right? So by considering that thin film, that is wedge-shaped film, we have calculated the fringe width. Yes, do you remember this derivation part? This is nothing but wedge-shaped film by considering a small thin wire inside the two plain glass surface or plain glass plate. And then we have derived the expression for fringe width, right? By considering the condition for dark fringe. That is mu 2 mu t cos r is equal to n lambda. So by considering this equation, we have derived that is fringe width is equal to wavelength of light source, that is lambda divided by 2 into theta, or we can simply say that is here beta is equal to lambda into L divided by 2D. So this is the formula for fringe width here, lambda L divided by 2D. See, actually in Young's double slit experiment also we have derived the formula for fringe width. So don't confuse with these two value formulas, right? So now we'll continue. See, once we see that experimental procedure, we'll move on to the problems. So this is about air wedge experiment, right? See, actually the experimental setup is nothing but you need one traveling microscope. Have you seen before traveling microscope? Have you heard? At the end of this unit, we are going to study some optical instrument. Have you heard this traveling microscope? தெரியுமா traveling microscope பார்த்திருக்கீங்களா கேள்விப்பட்டிருக்கீங்களா?
Yes, ma'am.
Yes. So this maybe in first year Young's modulus experiment, you might have used this instrument, traveling microscope, right? So we need this traveling microscope and we need one monochromatic light source, right? So here it is placed inside the wooden box, right? So that the light beam will come out like this. So what is about our, see actually previously we have considered this wedge-shaped film by considering two plain glass plates. Yeah, wedge-shaped film ke ipo nam enga porudhu. So we have these two instruments. That is, one is sodium, monochromatic source, which is nothing but we are using mostly sodium vapor lamp. Another one is traveling microscope. Third one is we need that film, that air wedge film. இல்லையா அந்த film வேணும். So இங்க பாத்தீங்கன்னா ஒரு பாக்ஸ் மாதிரி இருக்கும். இங்க ஒரு சின்ன ஒரு glass stand மாதிரி இருக்கும். In that we have to place that wedge-shaped film, which means ரெண்டு plain glass plates கொடுத்திருப்பாங்க. It is not visible here. இதுக்குள்ள நம்ம உள்ள இங்க insert பண்ணணும். இங்க இந்த ஸ்டாண்ட்ல நம்ம இங்க வைக்கணும். ஹரிசான்டலா இங்க வைக்கணும். So இந்த ஷேப்ல அந்த wedge-shaped இருக்கு இல்லையா அந்த ஷேப் நம்மளால பார்க்க முடியாது. See, actually with the naked eye, it looks like what two plain glass surface tied together. அப்படிதான் தெரியும். Because we are using very thin wire in between. Thin wire like a small hair. Hair ஓட நம்மளோட human hair ஓட thickness எவ்வளவு இருக்குமோ அவ்வளவுதான். அந்த அளவுக்கு thickness உள்ள ஒரு wire தான் நம்ம உள்ள insert பண்ணிருக்கோம். அதாவது ஒரு எண்ட்ல rubber band போட்டிருக்கோம். At certain distance from the tied end, we are placing that small wire, right? So it will form the film, right, in between these two glass plates. So if they place பண்ணதுக்கு அப்புறமா you switch on the light. Yes, so actually we are using some lens to converge the light beam. Suppose say for example convex lens we are using to converge the light beam, or else I can use straight away. So the light beam will come to the glass plate, that is a wedge-shaped film, and then this reflected light and the transmitted light will seen through this traveling microscope. Yes, with the help of this eyepiece, see we have to focus like this. In the மாதிரி traveling microscope arrange பண்ணிக்கணும். So in traveling microscope we have two scales. One is horizontal scale, the another one is vertical scale. In this experiment, we are going to consider only this horizontal scale. In horizontal, it has both main scale and smaller one vernier scale. See, actually traveling microscope la ரெண்டு scale இருக்கும். இது வந்து vertical scale. இப்படி இருக்கு இல்லையா? This is called vertical scale. Vertical scale, it has two scales. That is, one is lengthy, one is main scale. Here you'll be having that small scale that is called vernier scale. So in horizontal also same thing. This lengthy one, in horizontal, this is called main scale, horizontal main scale. Here in between there is one small rectangular shape. This is called vernier scale, right? So we are going to find out that interference pattern through this traveling microscope after the interference of these two waves, that is reflected and transmitted waves. In the light beam la irundhu shaped film la pattu vara and the rendu rays interfere aagi, we are going to see that interference pattern. So this is about the experimental procedure. Actually, in this experiment, we have two tabular columns, two parts to find. First one is to find the average bandwidth, right? Mean bandwidth or fringe width. We are going to calculate. The next one is to find the length or thickness of, length of this plate, air wedge shaped plate. That is from the tied end to the wire, thin wire. The glass plate la ஒரு எண்ட்ல வந்து நம்ம tie பண்ணிருக்கோம் இல்லையா? So அதுல இருந்து thin wire நம்ம insert பண்ணிக்கலாம். அதுக்கு நடுவுல இருக்கிற distance we have to, that length we have to find out. That is your second part of your experiment. So first part, so look at here. So I have focused here. So I have to keep it in some distance between this source and this traveling microscope or this wedge-shaped film. At particular distance only I can able to see that. Similarly, the light beam வந்து கரெக்டா இதுல பட்டு எனக்கு இங்க தெரியணும், right? அந்த மாதிரி டைரக்டா நான் அத ஃபோக்கஸ் பண்ணிக்கணும். So once I get that fringes patterns in this traveling microscope, I can start. That is, so many rings or bright and dark fringes will be formed. இப்படி ஸ்ட்ரைட்டா உங்களுக்கு fringes தெரியும். So you have to go in the middle may be dark-ஆ இருக்கும், right? So middle part போயிட்டு you just move on to the say for example in this tabular column we have calculated for n plus 30. So first dark fringe வந்து after this central fringe I am considering first one as n. Then next one, instead of taking n plus 1, I am using here n plus 3. Why? Means there is no much difference between n and n plus 1. Are you able to follow? Yes? இப்போ லைன்ஸ் வந்து பாத்தீங்கன்னா ரொம்ப க்ளோசரா இப்படி வருது இல்லையா? லைன்ஸ் பேட்டர்ன்ஸ், இந்த இன்டர்ஃபரன்ஸ் பேட்டர்ன்ஸ் வந்து லைன் நீங்க இமேஜின் பண்ணிக்கோங்க, அப்படியே ஒரு வெர்டிகலா அப்படி ஒன் பை ஒன் பக்கத்துல ரொம்ப க்ளோசரா இருந்ததுன்னா we cannot differentiate these two lines, right? So n-ஐயும் n plus 1-ஐயும் I cannot differentiate. That's why I'm taking 3, n plus 3 difference வச்சு நான் எடுத்துக்கிறேன். So instead of taking from middle to the last line, I'm just move on to the particular lines first. So either side you can move, left or right side from the central fringe. So here you can move to n plus 30. That will be in experimental procedure, that will be easy. So இங்க இருந்து நீங்க n plus 30 first count பண்ணி போயிட்டீங்கன்னா, then or else you can start from here also, any side. Middle central fringe la irundhu you have to count for n plus 3. So here you will be having, this is your microscope, traveling microscope reading, which consists of both main scale and vernier scale coincidence, right? Main scale reading and vernier scale. This is nothing but total reading. Total reading means vernier scale reading into least count, then add with main scale reading. Yes, least count of traveling microscope. I think here it is not mentioning here. So least count of, see, for any instrument there is a least count. For in case of screw gauge or vernier caliper, அதுக்கு ஒரு least count ஒன்னு நம்ம find out பண்ணிருப்போம், right? அந்த இன்ஸ்ட்ருமென்ட்க்கு. So இந்த traveling microscope பாத்தீங்கன்னா 0.001 centimeter. That is your least count of traveling microscope. So how we are getting these values, both MSR, that is main scale reading, and vernier scale coincidence. So after placing this wedge-shaped film, after getting the interference pattern, I am moving that first fringe, that is called as N. Nth fringe க்கு நான் வந்து I have to coincide with the lens crosswire. Lens crosswire எப்படி இருக்கும்? It's like a plus symbol, right? Students, are able to follow what I'm saying? Yes?
Yes, ma'am.
Yes. So lens crosswire kuda you have to coincide with the first line, first fringe of that is vertical cross wire, right? Vertical line of cross wire. So you have to coincide. Then you have to take this main scale reading in this horizontal scale. In this horizontal scale, you have to count that. See, actually in this vernier scale, you'll be having 1 to 50 divisions in vernier scale, right? In main scale reading, each division is 0.05 centimeter. Each division is 0.05 centimeter. So first division is 0.05 means at the division. That is next division is 0.1. Next 0.15, 0.2, 0.25, 0.3. Like that we have to count. So here this 0 of this vernier scale coincides which division in main scale? That is your main scale reading. அதாவது this 0 of vernier அங்க ஃபர்ஸ்ட்ல ஒரு லைன் மார்க் பண்ணிருக்கோம், ஒரு arrow mark 0. அந்த டிவிஷன் இந்த மெயின் ஸ்கேல்ல எந்த ரீடிங்க பாயிண்ட் அவுட் பண்ணிருக்கோ that is your main scale reading, right? So here it is mentioning about 13.15. Yes, 13 point. See, the reading will be like this because each reading is 0.05. So I am getting 13.15. Suppose the 0 of vernier scale is in between any two readings of main scale means take the previous one or take the crossed value. ரெண்டு ரீடிங்க்கு நடுவுல இருக்கு. Say for example 13th divisionல இருக்கு. What is the next reading of 13? Next reading என்னது? 13க்கு அப்புறம் உள்ள main scale reading என்னது? 13.05. You have to add 0.05, right? So next division என்னது? 13.1. Next division 13.15. Suppose that 0 of vernier scale is in between 13 and 13 kapra ulla next division means I have to take 13 only if it is in between any two readings. So here if it is showing the exact reading means take that particular value as main scale reading. So here I have taken this main scale reading. Now, so for the same fringe, I have to take again the vernier coincidence also. So both readings I have to take for first fringe. So after taking this main scale reading, I have to go for vernier scale coincidence. Out of this 50 divisions in vernier scale, which division is exactly coincides with the main scale? See, main scale, vernier scale, I told you that there are 50 divisions are there. Out of 50 divisions, any one line, ஏதோ ஒரு லைன் வந்து பாத்தீங்கன்னா அப்படியே ஸ்ட்ரெயிட்டா இதுக்குள்ள சி நம்ம நேக்கடையில பார்க்கும்போது எல்லாமே ஆல்மோஸ்ட் கோயின்சைட் ஆகிற மாதிரி தெரியும். பட் வித் த ஹெல்ப் ஆஃப் லென்ஸ், magnifying lens நீங்க யூஸ் பண்ணி பாத்தீங்கன்னா you will get to know that any one division which is exactly coincides with the main scale. So that division alone we have to take. It is not comes under fractional value. So full numbers தான். So already told you vernier scale 1 to 50 divisions ன்னு சொல்லிருக்கேன். So which division is exactly coincides? So this is around 26 first reading. Then I'm just taking the total reading by considering this B.Sc into least count of traveling microscope. Do multiplication first, then add with main scale reading. So you will get this. Likewise, we'll move on to then how to move the fringes means you will be given some screws, right, at the side of this traveling microscope here. Yes, here you'll be having two screws. One is for random movement. Another here you will have another screw that is for very minute left and right movement. இங்க இருக்கிற பெரிய screw வந்து ஈஸியா மூவ் பண்றதுக்கு யூஸ் பண்ணிக்கோங்க. But when you take the readings for minute, because each fringe is very minute. அப்ப அந்த reading எடுக்கும்போது we are just using this screw to move this traveling microscope left to right or right to left, any direction. But once you start from left to right means you have to follow the same order till the end, right? So if I end, then I have to count the fringes by looking through this traveling microscope eyepiece. இதுல பார்த்துக்கிட்டே நான் இங்க adjust பண்றேன் so that I can count the fringes from end. எண்ணுக்கு அப்புறம் ஒரு 3 fringes நான் count பண்ணி அதுல coincide பண்ண வைக்கிறேன் lens cross wire. Then I am taking this both values MSR and B.Sc, right? So similarly, I am taking up to n plus 30, n plus 3 n 6 n 9 n அந்த மாதிரி ஃபுல்லா எடுத்துட்டேன். So then after that I am just doing the total reading. Then next part, this calculation is nothing but width for here I am just considering for 12 fringes. Yes, so 12 fringes means இங்க இருந்து இதுக்கு நான் எவ்வளவு டிஃபரன்ஸ், அது மாதிரி 3 ல இருந்து 15க்கு எவ்வளவு டிஃபரன்ஸ் by considering 12. அப்போ அதுக்குள்ள வேல்யூ டோட்டல் ரீடிங் வேல்யூ இருக்கு இல்லையா, அது ரெண்டுத்துக்கும் நான் டிஃபரன்ஸ் எடுக்கிறேன். I'm just finding the difference, don't bother about the sign, right? So any number, from any number you just find the difference. So I'm getting this value. So this is for 12 fringes, right? So each value for one fringe means each value divided by 12. So after that, you just take the average of these values. So I'm getting what? 3, 4, 5, 6, around 7 values I have got. So after taking these values, you find the average. So mean bandwidth is like this. In terms of meter, I have noted. Right. So second part is nothing but after taking this, you just move on this traveling microscope, that is eyepiece, to the left side, that is rubber band tied end side. அதுக்கு இந்த ஹரிசான்டலா இந்த டிராவலிங் மைக்ரோஸ்கோப் இது வந்து ஆக்சுவலி மூவபிள். இப்படி ஹரிசான்டலா இந்த பார்ட் இருக்கு இல்லையா, மேல இருக்கிற பார்ட் இது இல்ல, இந்த மேல இருக்க பார்ட் வந்து லெஃப்ட் அண்ட் ரைட் மூவ் பண்ணிக்கலாம். ரைட். ஸோ இப்போ இதை நான் மூவ் பண்ற அந்த வெட் ஷேப்டு ஃபில்மோட டைட் எண்ட் இருக்கு இல்லையா, அதோட லெஃப்ட் சைடு மூவ் பண்ணி யூ ஜஸ்ட் coincides with the cross wire after getting that tied end position in eyepiece of traveling microscope. So you just focus that after getting this coincides with the rubber band end, then you take the values. That is here it is mentioning, right? Rubber band, what is MSR and BC. One reading alone we are going to take because we have to find the distance between these two ends, tied end and the wire, thin wire placed. Enga place pannirkumo adu rendukulla in between distance, right? So here it shows some value MSR and BC. Similarly, you move this traveling microscope to the opposite end, that is on that thin wire position. Hair, அங்க hair in போட்டுக்கோங்க. Thin wire we have used here is human hair. So அந்த எண்டுக்கு focus பண்ணி, I mean coincide பண்ண வச்சுட்டு then you take both MSR and BC reading, right? So after taking this value, you will get that what length of the wire. It is around 0.341 into 10 power minus 2 meter of centimeter I'm getting. So after that, we know that formula we have derived. Beta is equal to lambda by 2 theta. So from this we can able, beta is equal to what? Lambda L by 2D. So we know that remaining values, beta value we know that L also we know that, and then substitute in the formula. Yes. So here lambda is nothing but wavelength of the monochromatic source which we have used. So here we have used that sodium vapor lamp. Its wavelength is constant 5893 Armstrong, right? In terms of meter means it is 10 power minus 10 meter, right? So L is in terms of centimeter I have mentioned, in terms of meter I have mentioned here, and then beta value, this average value, right? After getting from this first tablet column. So substitute everything is in the formula so that we can able to find the T is nothing but thickness of that thin wire. So thickness of thin wire we can able to calculate. See how much the thickness of human hair, around the thickness of, it differs from every human, right? So average we are getting that thickness of wire is around 59 or 60 micrometer. Micro means 10 power minus 6. So I'm getting around 60 micrometers. So this is about the experimental procedure of air wedge to find the thickness of wire. Is it clear? Yes. So next we'll see some problems. So first problem, see in this unit, only one topic is pending. After seeing this problem, we'll move on to actually Michaelson interferometer, right? So after seeing these problems, we'll move on to that. So first problem, a source of red light, that is lambda value is given. It is around 7000 Armstrong. So in terms of meter means it is 10 power minus 10 meter, right? Which produces interference through two narrow slits spaced at a distance of 0.01 centimeter. Question is, at which distance from the slits should a screen be placed so that the first few bands are spaced 1 centimeter apart? So go through the problem. This is about the which part? Young's double slit part, right? So given data from the problem, you just write what are the data given. So lambda is given 7000 Armstrong, and then separation is given. This, that is 0.01 centimeter. Yes, separation between two slits. It is 2D we have used. In some other book, it is straight away gives simply D. D nu kuduthirupanga or 2D nu kuduthirupanga, right? So it is 0.01 centimeter. And then it is given 1 centimeter apart, which is the bandwidth. So beta is equal to fringe width or bandwidth. So it is 1 centimeter. Our aim is to find what? Distance from the slit. So capital D alone we have to find. That is slit and the screen enga place pananonu ketirukanga. So formula is, that is beta is equal to lambda D divided by 2D. See, read the question so that we can use this formula. This is from Young's double slit experiment, this formula. Beta is equal to lambda into D divided by 2D. In some other book, instead of this 2D, they will give straight away simply D. So we can use anything. So from this, our aim is to find D. So substitute all the values. So 1 into 0.1 divided by this 7,000 in terms of centimeter I have converted. So you will get the value is around 1.43 meter, this capital D value. Similarly, next problem. So two plain glass surfaces in contact along one edge are separated at the opposite edge by thin wire. If two interference fringes are observed between these edges in sodium light of normal incidence, what is the thickness? Thickness which is nothing but, so which formula we have to use? First write the given data. See, for air, mu is 1. It is the constant refractive index of air. And then here, read this. It is normal incidence. Normal incidence. So R is equal to 0 degree. Angle of refraction. There is no. Inga pass between two medium pass agudina. Inga angle of refraction is 0. It is understood along the normal. Obviously, the value you substitute, this 0 you have to substitute in this value. Cos R is equal to 1. That is cos 0 is equal to 1. Right? Now, N is equal to 20. That is, here it is given, if 20 interference fringes, number of interference fringes are given, N is equal to 20. And then wavelength of the light, it is lambda is equal to 5890 because we are using sodium vapor lamp. So this value is constant, 5890. Now formula is what? 2 mu T cos R is equal to N lambda. This is for bright fringe. 2 mu T cos R is equal to N lambda. Now substitute everything in the formula. So 2, this refractive index value, we have considered this medium as air. So 1, the refractive index value is 1. T is T into, because this T alone we have to find out, into cos R, obviously it passes through normal incidence. So this value is also 1, which is equal to N is 20 and into lambda value is constant. Then you multiply this, you will get this value is around 58 micrometer. 50 thickness is 58, thickness of the wire, 58 micrometer. So depends on the problem, we have to choose the formula, right? What are the given data? From that only we have to choose. So again, two more problems. So in this Young's double slit experiment, two parallel slits are made 1 millimeter apart. 1 millimeter means it is 1 into 10 power minus 3 meter. And then screen is placed 1 meter away, right? So capital D value is also given 1 meter. And then what is the fringe separation when the blue-green light of lambda is equal to this thing, 500 nanometer. It is not clear here. It is nothing but 500 nanometer is used. So formula is beta is equal to D lambda by, here you can write is 2D, the separation between two slits, right? 2D. Or else you can use D also. So 2D is equal to 1 millimeter. 2D, separation between two. Other 1 millimeter, right? So I can write 1 into 10 power minus 3 meter. In terms of meter, I'm just converting. Similarly, D, capital D, between screen and slit, it is 1 meter, right? And then lambda is equal to 500 nanometer. Convert into meter. 1 nanometer is equal to 10 power minus 9 meter, right? So 500 into 10 power minus 9 meter. Substitute in the formula, beta is equal to this D value into lambda divided by small d value or 2D value. This is simply 1 into 10 power minus 3 meter. So simplifying this, I am getting 0.5 millimeter or 0.5 into 10 power minus 3 meter. So this is my fringe width, right? And then next problem. Interference fringes are produced in the focal plane of an eyepiece at a distance of 50 centimeter from the slit. Separation between two images obtained for the two positions of convex lens are this one and this one. That is 10.33 millimeter and 0.43 millimeter respectively. If lambda, that is wavelength of light I'm using is 6300 Armstrong, find its bandwidth. Bandwidth or fringe width calculate per. Obviously, beta alone we have to calculate. What are the given data here? Formula is same. Beta is equal to d lambda by 2d. But here, see this d value. See, d value is capital D value is given. It is 50 centimeter. Similarly, lambda value is given 6300 Armstrong. But it is not given. 2D value is not given. Instead of that, it is given to position of convex lens, right? Which means D1 and D2 values are given. See, I have told this formula while taking that interference procedure. This 2D is equal to square root of D1 and D2, right? So from this value, we can find 2D, then substitute in the formula. So you will get what after substituting these values, I'm getting beta is equal to 0.014 centimeter. So this is about the bandwidth or fringe width. So that's all about these part, and that is Young's double slit experiment, Fresnel biprism, and then path difference in thin film, that is reflection as well as transmission, and then wedge-shaped film theory as well as the experimental procedure, and we have seen some problems. The last topic in second unit is Michaelson interferometer. So we'll see the principle, construction, working, and then what are the types of fringes formed in this Michaelson interferometer, and then what are the applications. Then we'll move on to next unit. So actually this interference and diffraction unit will be looks like lengthy units. Yes, so you have to understand the basic concepts. Then the remaining blocks, fourth and that is polarization about fourth and fifth block is quite easy. All like a story madri, fourth and fifth block வந்து easy finish பண்ணிடலாம். So now let's see about this Michaelson interferometer. So idhula principle பார்த்தோம்னா it works on the principle of interference, right? Interference of light waves. So அதுக்கு தான் நமக்கு application Michaelson interferometer. Now come to the construction. Look at the diagram here. This is the interferometer, Michaelson interferometer ஒரு general diagram, right? So என்ன இருக்குங்க generally it consists of a source, monochromatic source, SS source. Here I am just using one convex lens. This L represents convex lens. Excuse me. Then I'm using one telescope. Excuse me. So I'm using one telescope, and then I'm using two glass plates, namely G1 and G2. Yes, glass plates and mirrors M1 and M2 I'm using, right? So these are the general parts of this Michaelson interferometer. Now come to the construction part. So it consists of, I told you, it consists of a monochromatic light source. So we have used one convex lens. Why we are using this convex lens? To get the parallel beam. See, usually whenever we are using any source, light வந்து எல்லா சைடும் இப்படி ஸ்கேட்டர் ஆகும் இல்லையா, இந்த மாதிரி ஸ்கேட்டர் ஆகும். அப்போ எனக்கு அதை கரெக்டா கன்வெர்ஜ் பண்ணி எனக்கு parallel நான் கொடுக்கணும்னா I have to use convex lens. Convex lens வந்து கன்வெர்ஜ் பண்ணி நமக்கு அதுல இருந்து parallel beams கிடைக்குது. So that I'm using here. And then here I'm using, it consists of optically plain glass plates, that is flat glass plate called G1. This glass plate first thing, yes. So this G1 is semi-polished, silvered at the back. So under you just underline this, it is semi-silvered at the back side of this glass plate. So two plane mirrors, namely M1 and M2. I'm just using M1 and M2, which are mounted vertically on two arms at right angles to each other. இது ரெண்டு பாத்தீங்கன்னா perpendicular இருக்கும். This M1 and M2. This G1 is called beam splitter. In the G1 glass plate, it is called beam splitter. So in the angle I have to keep at 45 degree. Yes, to both AM1 and AM2. That is, the ray is coming from this light source. In the light beam the ray varudhu. So in the glass plate la padra in the point A represent பண்ணிருக்கேன். So this mirror is M2, this one is M1. This is fixed mirror. This we can able to move the upside one. This M1 movable mirror, right? So this AM1, AM2 வந்து பாத்தீங்கன்னா that is 45 degreeக்கு இங்க இருக்கிற மாதிரி இந்த AM2க்கும் AM1க்கும் இருக்கிற மாதிரி I have to place this glass plate G1, right? So these two M1 and M2 have 3 leveling screws at the back. இங்க பாத்தீங்கன்னா ஒரு screws இருக்கு. Back side you will be having some screws. And G2, I'm introducing another glass plate, namely G2. It is called compensating plate. I'll just tell you later why it is mentioning. I mean, why I'm calling this as compensating plate. G2 நான் compensating plate ன்னு ஏன் சொல்றேன்னு நான் next construction. I mean, theory ல நான் சொல்றேன் workingல. Right. So this G2 பாத்தீங்கன்னா which is similar to G1 plate, right? So இங்க நான் அதே angle இங்க எப்படி நான் 45 degree வச்சிருக்கனோ அதே மாதிரி I'm just placing here. So after reflection from these two rays, in the rays after reflection from AM1 as well as from AM2, yes, from these two mirrors M1 and M2. So here by looking through this telescope, I can able to see that interference patterns, that is alternate bright and dark fringes will be formed. So it can be seen through this telescope. புரியுதா? So light ray source ல இருந்து இங்க வருது, glass plate G1 வச்சிருக்கேன். இங்க இருந்து இந்த workingல நான் சொல்றேன். இப்போ நான் next page turn பண்ணிடுவேன். See, whenever we are using the another medium, from one medium light travels to the interface of another medium, obviously it will undergo refraction. Is it clear? இங்க glass plate தான் நான் வச்சிருக்கேன். உள்ள refraction ஆயிட்டு திரும்ப transmit ஆகுது. Right? See, இங்க வரும்போது எனக்கு பட்டு இங்க ரிஃப்ளெக்ட் ஆகுது. இங்க இந்த டைரக்ஷன்ல போகுது. AM1 டைரக்ஷன்ல போயிட்டு இந்த மிரர் M1ல பட்டு எனக்கு ரிஃப்ளெக்ஷன் நடக்குது. ரைட்? ஆனா இங்க பாத்தீங்கன்னா இங்க போயிட்டு இதுல ஆக்சுவலி 3 டைம்ஸ் எனக்கு வந்து மீட் ஆகுது. ஆனா இந்த ரே பாத்தீங்கன்னா AM2 only once தான். First you just ignore this glass plate G2. ரைட்? இதுக்குள்ள பாஸ் ஆகுறது பாத்தீங்கன்னா ஃபர்ஸ்ட் இங்க வருது. இங்க இருந்து திரும்ப எனக்கு இங்க போகுது பார்ட் ஆஃப் த பீம். So ஒரு டைம் இங்க வருது, செகண்ட் டைம் இங்க போகுது, தேர்ட் டைம் இந்த பீம் ஸ்பிளிட்டரை cross பண்ணுது. It passes 3 times. That is AM1. But whereas in the case of AM2, it passes only once. ஒரு டைம் இங்க ரிஃப்ராக்ஷன் நடந்து இங்க போகுது இல்லையா, அடுத்த டைம் பாத்தீங்கன்னா இது திரும்ப இங்க மிரர் M2ல பட்டு it reflects back, right? So it retraces its own path. இதேதான் திரும்ப அதே பாத்ல வருது. வந்துட்டு the back side it is semi silvered, right? So inga பட்டு திரும்ப reflect ஆகுது. It cannot pass through this G1. Just this interface la பட்டு reflect ஆகி இங்க வருது. So இது 3 times இங்க வந்து pass பண்ணுது இந்த glass plate. இந்த ray பாத்தீங்கன்னா only once தான் pass பண்ணுது. That's why I'm using this compensating plate to get the optical paths equal. இந்த optical pathம் இந்த optical path equalize பண்றதுக்காக I'm just using this G2, that is compensating plate. So இப்போ பாத்தீங்கன்னா இந்த பிளேட்டுக்கு அப்புறம் ஃபர்ஸ்ட் இங்க வரும்போது ஒரு டைம் கிராஸ் ஆகுது, ரைட்? ஸோ செகண்ட் டைம் பாத்தீங்கன்னா இங்க திரும்ப கிராஸ் ஆகுது, திரும்ப இதுல பட்டுட்டு திரும்ப போட்டு இங்க கிராஸ் ஆகி வருது. ஸோ 3 டைம்ஸ் இப்போ டாலி ஆயிடுச்சு AM1 and AM2, right? So now come to the working part. So again same thing. So consider a monochromatic light source. So we are using the convex lens to get the parallel beam. First, initially it falls on the first plate, that is beam splitter G1. Now the beam is divided into 2 parts. Idhula pattadukku apparama, after falling on this glass plate G1, it is divided into 2 parts. One is reflected along this one, another one is transmitted along this side, right? So 2 parts. One is reflected along AM1, another one is along after refraction. It is transmitted along A2, second part. Now, this reflected part that is along AM1, which falls on first mirror M1 normally. So it is reflected back again. It travels along its original path. In the way eppadi pocho, inga reflect aayittu, inga M1 la patte reflect aayittu, again it follows the same path, right? So original path. Then it passes through G1 once again and then produces proceed to AT. AT is nothing but your telescope, this direction. After reflection, it passes through G1, then it comes to, this ray comes to, we can able to see through telescope, right? Similarly, now consider the second part. Transmitted beam is incident normally on second mirror M2. Therefore, it is reflected back along its original path like your previous ray AM1. Again, it suffers reflection at lower surface of G1. See, இங்க வந்து படும்போது this lower surface of G1 reflection takes place. Yes, அப்பதான் இங்க பட்டு திரும்ப telescope வருது. His reflection takes place and then it proceeds to AT. Yes, now the telescope receives these two light rays from the source, that is SA. So now the interference fringes will be produced, that is alternate bright and dark fringes will be seen through this telescope. So now ray AM1 passed through this beam splitter 3 times. I told you, no? In the previous AM1 in the glass plater 3 times passed. Whereas this one, without considering the second plate, it passes through only 1 time. That's why we are using that compensating G2 நம்ம introduce பண்றோம். So the optical path equal நம்ம கொண்டு வருது, right? So same அதே G2 பாத்தீங்கன்னா G145 இருக்கணும். Similarly G2 same angle we have to keep. So this whole arrangement is similar to interference pattern absorbed from 2 reflecting phases, namely M1 and M2 dash. Where M2 dash பாத்தீங்கன்னா இங்க இருக்கு இல்லையா, M2 dash is nothing but virtual image of this M2 mirror. Here I am getting this M2 dash. Now this forms the air film. That is 2 reflecting phases M1 and M2, which enclosing an air film. Right. So from this we can able to find what the path difference between 2 interfering rays. It arises due to what? So whenever we have 2 rays during interference, we have to find the path difference, right? So path differences, one is due to difference in distance of M1 and M2 from G1. இங்க இருந்து இதுக்கு எவ்வளவு தூரம் போயிருக்கு, G1ல இருந்து M1க்கு எவ்வளவு தூரம். So இந்த ரெண்டு டிஸ்டன்ஸ், அந்த டிஃபரன்ஸ் இருக்கு இல்லையா, அந்த டிஃபரன்ஸ்னால நமக்கு பாத் டிஃபரன்ஸ் கிடைக்கும். The second one is from ray M2 to G1. That is from this one also I have told you while taking that path difference in reflection, right? Rarer to denser medium means obviously the path difference or phase difference. Phase difference it takes at pi path difference will occur. Phase difference. Path difference is நமக்கு lambda by 2 னு சொல்லுவோம். Yes, by considering the wave. Yes, do you remember that? Phase change of pi we have to include. This is under the case of rarer to denser medium, when light comes from rarer to denser medium. So path difference between 2 interfering rays, in this case, it arises due to these things. First thing is difference in distance of M1 and M2 from beam splitter, first plate, glass plate G1. Similarly, second is from ray M2 to G1, that is rarer to denser medium. Phase change of pi takes place. Our path difference means lambda by 2 we have to consider. And then in telescope, we are seeing that interference patterns, that is alternate bright and dark fringes. It will be found or observed in the focal plane of the telescope. So these are the working of Michaelson Interferometer. Now come to the types of fringes. So what are the types of fringes found in Michaelson Interferometer? See, there are 3 types of fringes. First one is circular fringes. Second one is localized fringes. Third one is white light fringes. So come to the circular fringes. So it is produced. This type of circular fringes na ipdi irukum. நமக்கு தெரியும் இல்லையா? It's somewhat similar to Newton's rings, but not exactly Newton's ring. Newton's ring பார்த்திருக்கீங்களா? Newton's ring படிச்சிருப்பீங்க தியரி. So இந்த மாதிரி circular இப்படி தான் இருக்கும் rings, but it is not Newton's ring. ஏன்னா கொஞ்சம் டிஃபர் ஆகும். So it is produced when these 2 mirrors M1 and M2 dash are parallel. அதாவது இங்க இருக்கிற the virtual image of M2, ஏன்னா இங்க தான் நமக்கு அந்த air film form ஆகுது between M1 and M2 dash, right? So these 2 are parallel இருக்கும்போது, yes, so when M1 and M2 dash are parallel, circular fringes will be produced. Now just consider if the distance of M1 and M2 from first beam splitter, that is G1, It differ by the distance small d means. So separation between these two mirrors is given as 2d. Some book it is given 2t, right? 2d கொடுத்திருக்காங்க. The air film நடுவுல அந்த M1 and M2 virtual image ரெண்டுத்துக்கு நடுவுல இருக்கிற space 2d or separation. Now the path difference between two beams is 2d cos theta, which we know already. So now circumference of the circle, that is we have considered the angle of theta, that is angle theta on I. So by considering the rings satisfy the condition of maxima, that is 2d cos theta is equal to n lambda, which is for bright fringe. 2d cos theta for is equal to n lambda for bright fringe. As well as for minima, it is 2d cos theta is equal to 2n plus 1 into lambda by 2. This is for dark fringe, or simply we can say that destructive fringe. Right. So alternate bright and dark fringe will be formed. Rings, not fringes. That rings will be formed because we have that is circular fringes alone formed by considering these two mirrors are parallel, these two position M1 and M2 dash, right? So here it looks like a similar or resemblance to Newton's ring, but these rings differ from Newton's ring in origin. So it is called fringes of equal inclination in this type, in this Michaelson Interferometer circular fringes. And also it is called Hegner types of fringes. Then what is the difference between Newton's ring? Newton's ring resemblance resemble, but it is not exactly Newton's ring. It differ in origin. So Newton's ring produce it is convex lens we have used with the large radius of curvature, which is placed on plain glass plate, so that air film is formed between or glass plate convex be curved, right? So we have to keep that. So air film is formed in between, that is upper surface of plate, glass plate, and lower surface of that convex lens. So in between air film is formed. Now that is when it is exposure to monochromatic light source, we will get alternate bright and dark fringes in this apparatus, that is by considering convex lens and glass plate. So here fringes, after getting that concentric rings, the Newton's ring, right? So this when move away from the center, the spacing between the previous equal inclination, so like fringes of equal inclination. But here when move away from the center fringes or rings, means the spacing between the rings will be decreasing. And what is the cause of this Newton's ring means? It is formed due to interference between light waves reflected from top and bottom surface of air film, which is formed between lens and glass plate. So this is the cause of Newton's ring, but this is not given in your syllabus. You just try to understand, because here the rings which we have got is totally different, somewhat similar, but it is not exactly what Newton's ring, right? That's why I'm telling. So first type of fringe is circular fringe. Second type of fringe is localized fringe. In this localized fringe, we have three cases. Say when M1 and M2 dash are inclined to certain angle. Ipo in the madri M1 in the madri irukku. The straight line shows that position of M1 mirror, right? This dotted line shows that what virtual image of M2. In three cases, in the dotted line shows that virtual image of M2 position, mirror M2 position. So air film is enclosed in wedge-shaped film, therefore localized fringe will be formed. Idellame localized fringes, but cases are there. See, for first case, because case 2 and case 3 somewhat similar. So in case 1, we are getting straight fringes. But that is a case, there is a condition to get this straight fringes. If in the madri vertical straight fringes venuna, condition is there, that is in the M1 intersect M1 intersect M2 dash in the middle. Yes, M1 in the middle intersect we will get straight fringes. Right. In case 2 and case 3, it looks like curved fringes, convex madri curved fringes. But on the curved, one is facing towards left side, another one is facing towards right side. In the madri kadikkudu. So there is a case. So here, if M2 dash, virtual image of mirror M2 lies below of M1, இந்த M2 dash வந்து M1 க்கு கீழே இருந்ததுன்னா இப்படி ஃபேஸ் பண்ணி curved fringes will be formed. Okay, so in next case பாத்தீங்கன்னா this M2 dash வந்து virtual image வந்து மேல இருந்ததுன்னா M1 mirror க்கு மேல இருந்ததுன்னா we are getting the image like fringes like this which face towards the right side. Previous one left side face பண்ணிருக்கும், இது right side face பண்ணிருக்கும். So these are called localized fringes. But most of the times we are using this straight fringes alone. So M1 should intersect M2 in the middle or center. And then third one is called white line fringes. So when white light is used means fringes absorb when the path difference should be small. Inga path difference kammiya irukumbodhu da we can able to find the fringes. So this type of fringes, that is white light straight fringes, is used for the determination of zero path difference. That is, I didn't mention here. It is used to find the zero path difference, right? So here it is depends on the central fringe is dark or white. It depends upon the whether the plate G1 is polished or unpolished. And the plate இது வந்து பாலிஷ்டா அன்பாலிஷ்டா இதை பொறுத்து தான் வந்து இந்த சென்ட்ரல் ஃப்ரிஞ்ச் வந்து பிரைட்டா டார்க்கான்றது இருக்கும். Right. That's all about the types of fringes. Next thing is about applications of Michaelson interferometer. First one is there are few applications. See, actually, so many applications are there. So out of that, only 2 applications alone we are going to discuss. And then third and fourth, just the topic alone given, right? Need not to explain in detail. So first application is to find the wavelength of monochromatic light source, right? First one is determination of wavelength of monochromatic light. So we know that with the help of Michaelson interferometer, we are getting circular fringes. Yes, circular fringes kedikidhu. Now telescope is focused on first fringes. Adukku nama focus panni vekirom. Now rotate the mirror or move the mirror M1, which is parallel to itself. Now fringes sweep across the field view. Field view ku adu vandu ungalku adu move agum in every displacement of lambda by 2 by moving this M1 mirror. M1 move பண்ணிட்டு இருக்கும்போது நமக்கு ஒரு bright fringe வந்து பாஸ் ஆகும் cross wire telescope ல. அப்போ ஒரு certain distance of this movement, the displacement of this M1, எத்தனை number of fringes வந்து cross ஆகுது field view க்கு. So we have to count. Say for example, if small m is the fringes move across. Yes, m is fringes move across means generally we are considering. Yes, when the mirror M1 traverses the known distance, I'm just considering the known distance is small l on the carriage scale. Now the formula is given m into, this is nothing but number of fringes crossed, right? So m into lambda by 2. This is about the displacement of M1. So lambda by 2, which is equal to known distance l. So from this relation, I can able to find what lambda, that is wavelength of monochromatic source. So 2l, yes, 2l is equal to m lambda, or lambda is equal to 2l by m. So from this relation, I can able to find the wavelength of monochromatic light source, right? And next thing is about determination of difference between doublets or resolution of spectral length, or else it is given difference in wavelength. Yes, determination of difference in 2 consecutive wavelengths, right? So in this case, so actually what we are going to consider means the spectral lines which we have got is not proper in some cases, right? And the lines வந்து நம்மளால resolve பண்ண முடியாது, ஈஸியா differentiate பண்ண முடியாது. Spectral lines are not separated. So only with the help of this Michaelson interferometer, by studying change of visibility of fringes with increasing path difference, this problem can be rectified. Now consider a light source S which emits lights of wavelength, consider lambda 1, lambda 2. அந்த மாதிரி emit பண்ணிட்டு இருக்கு. இப்போ lambda 1 corresponding-ஆ ஒரு fringes pattern produce ஆகும். Similarly for lambda 2 corresponding-ஆ fringes patterns will be produced. So due to this superposition, fringes are not clearly visible. Yes, superposition we can able to differentiate. So this problem can be rectified here. How? By when M1 is moved, mirror M1 is moved, these 2 sets of the fringes get in steps or out of steps alternately. Right? In step na bright fringe, out of step na dark fringe, right? On further movement of this mirror M1. First நான் கொஞ்சம் மூவ் பண்றேன். பண்ணும்போது பாத்தீங்கன்னா அந்த fringes, two sets of fringes get in step அப்படின்னா உங்களுக்கு அதை மூவ் பண்ணும்போது எனக்கு வந்து ஃபர்ஸ்ட் என்ன சொன்ன fringes are not clearly visible சொன்னேன், which means it's like looks like blur, right? இப்போ எனக்கு அது மேக்ஸிமமா பிரைட்டா இருக்கணும் அப்படின்னா so I have to move this mirror M1, right? So that இது மேல இது ஓவர் ஃபால் ஆயிட்டு எனக்கு அந்த பிரைட்னஸ், அந்த இமேஜ் இல்லையா, பிரைட் இமேஜ் இருக்கு இல்லையா, அது இன்னும் டிஸ்டிங்க்டா எனக்கு தெரியும், மேக்ஸிமம் பிரைட்னஸ்ல தெரியும், ரைட்? இது ஒன்ஸ் மேக்ஸிமம் பிரைட்னஸ் வந்ததுக்கு அப்புறமாவும் if you are moving the mirror M1 means you are getting that maximum darkness fringe, that is out of step. So alternate maximum bright fringe and alternate maximum dark fringe will be observed while moving this mirror M1, further movement of mirror M1. Right. So here just consider D is the displacement of mirror M1. In the M1 na move pandrele displacement at D nechukka for two consecutive position of maximum distinctness or indistinctness, which is nothing but maximum brightness or maximum darkness. And the separation displacement na D எடுத்திருக்கேன். Then path difference equal to 2D. Path difference of these two waves is given as 2D. If number of fringes of wavelength lambda 1, you know, because I have considered two wavelengths of light source, right? So number of fringes of wavelength lambda 1 lying in the path, it is denoted as simply n. Similarly, number of wavelength in lambda 2 lying in the path n plus 1. This is nothing but my consideration. n எடுத்திருக்கேன், right? Lambda 1 la number of fringes path la irukku n ன்னு எடுத்திருக்கேன். Next lambda 2 la irukku I am just taking n plus 1. Now 2D is equal to n lambda. Already I know that. Path difference equal to n lambda. So path difference equal to n. This is to differentiate first wavelength and second wavelength. This is for first case, number of fringes. Number of fringes in the first case, that is n. So 2D is equal to n lambda 1. Similarly, 2D is equal to this one by considering n plus 1. It is 2D is equal to n plus 1 lambda 2. So from this, in both case, you find what is n. So here straight away it is given n is equal to 2D by lambda 1. Here you just multiply with lambda 2 here. So n lambda 2 plus lambda 2. So from this n lambda is equal to take this lambda 2 to the opposite side. So 2D minus lambda 2, from this find n. N is equal to 2D minus lambda 2 by lambda 2, or else I can write 2D by lambda 2 minus this one is 1. By considering these two equations, that is this thing equal to this thing, right? Both will be similar. So 2D by lambda 1 is equal to 2D by lambda 2 minus 1. And just take this 2D by lambda 1 to the opposite side. Similarly, minus 1 to the left hand side. So I'm getting this equation. Then simplify this after taking the common term outside. 2D is common. I'm getting 1 by lambda 2 minus 1 by lambda 1 is equal to 1. So 2D into, take LCM here, lambda 1 minus lambda 2 divided by this thing, which is equal to 1. Or I can write, take this 2D to the opposite side. So lambda 1 minus lambda 2, take this denominator term also in the right hand side. So lambda 1, lambda 2 divided by this 2D. If lambda 1 and lambda 2 is equal to lambda square means your that is wavelength difference in wavelength, or I can write delta lambda is equal to lambda square by 2D. So from this, my aim is to calculate only the difference in wavelength or determination of difference between two doublets, right? So it is calculated now. That is delta lambda is equal to lambda square divided by 2D. So this method is also be used for to find whether the given source of light is monochromatic or not. So these two are the main applications. That is, first one is to find the wavelength of monochromatic light source. Another one is difference between the wavelength of light. And third one is determination of refractive index or thickness of thin films. So I'm not going to explain. And next application is calibration of standard meter. Also, we are using this Michaelson interferometer. One part is we are using Michaelson interferometer in last one, right? So that's all about second block, interference unit. And then diffraction, next unit, I'm going to start in next class. I mean, today by 12 o'clock we have another class, right? So on that time, I will start that diffraction. Here. So anyway, thank you, students. We'll continue in the next class by 12 o'clock.